All right, ladies and gentlemen, class recording has started. So, on Tuesday, the last half of the period, we talked about the idea of equilibrium. And got this little question over here on the side, right? What is the condition required for an object to be in equilibrium? And we talked about that an object is in equilibrium if the net force acting on that object is equal to 0. If the net force on an object is equal to 0, that means that it is now not accelerating. So we said that there can be two conditions that would be considered equilibrium. If something is at rest, that would be equilibrium because it's not accelerating. But an object moving with a constant velocity is also considered to be in equilibrium. If we looked at the forces, we would find that those forces all cancel out. It would continue moving because of the idea of inertia, right? That something that is already moving will continue moving. So just keep in mind, right, that equilibrium is something that's at rest, but it can also be something that's moving as long as it's moving with a constant velocity, and then inertia would just keep it going. Good there? On Tuesday, we started working a problem dealing with equilibrium, but we didn't get all the way through that problem. So what I wanted to do was we talked about this problem where this engine was hanging in the auto shop, but we didn't get all the way through it. So what I want to do is the next one that's at the bottom of that page that has this crane and this wrecking ball. I know. I noticed, like when I started this, it's like there's two chains at the top of this page and the wrecking ball at the bottom of this page. Like up until this year, neither of these problems was an issue, but this year.
Yeah, just do a little bit here.
I drew a person hanging so much better.
You can just do a stick figure. Yeah.
No, that might be even more demented than the actual. All right, so. I know, that's saying a lot. So.
Wow.
All right, so it says, I mean, if you guys want to do that, go, feel free, you know, so. All right, it says here, this wrecking ball is held in place by two steel cables. Oh, sorry. I wanted to start this problem from the beginning and work it all the way through, just so you can kind of see how all the parts fit together, as opposed to trying to remember what we did on Tuesday and pick it up from there. So let's just work it right from the beginning.
We didn't finish the example.
Right, like I said,
I'm just like, I'm thinking.
Yeah, we didn't finish. Wait, we didn't finish the one above it.
Yeah.
Yeah, this one is like almost exactly the same problem. So I just kind of want to work this one all the way from the beginning instead of having you try to jump back into that problem. So, all right. So it says, wrecking ball is held in place by two steel cables attached to a crane. The tension in cable A is 460 newtons. So two parts to this problem. First part says, what is the tension in cable B? And then the second part says, what is the mass of this wrecking ball? So remember, when we talk about tension, tension is just a fancy name for force. It's force that comes from like a string or a rope or something like that. But when it says what is tension, what it's really asking is what is force. So part A of this problem says, what is the force that cable B is exerting on this wrecking ball? So this one here is labeled as cable B, all right? And then the second part of this problem, right, what is the mass? Means we want to know what the mass is, right? Hopefully that one's pretty easy. So what is the tension in cable B, right? That's just the force of cable B. What is the mass? What's the mass? Okay. It did give us one piece of information directly, right? The tension in cable A is 460 newtons. So we know that cable A, the one that's labeled right here, right? The force that that cable is applying to the wrecking ball, 460 newtons. And then, even though they didn't say it in the problem, the picture here shows us that there's an angle, that this cable is making an angle of 40 degrees. So I'm going to call that theta B because it relates to the tension in B, right, the force from B. So we'll call that 40 degrees. Okay? Good there for starters? We've identified what we're looking for. We identified what information was given to us in the problem. The next step in doing this is a free body diagram. A picture that shows us all the forces that are acting on an object in a given situation. First force we'll put on there. Right? That force is going to represent gravity, right? So we said we'll label this F of G, right? And earlier in the week, we talked about how to calculate that force of gravity, right? How do we calculate the force of gravity acting on something?
9.81.
M times G, right? Or the acceleration of gravity times its mass. Now, in this problem, can we actually figure out what that force of gravity is? We can't because we don't know the mass of that object. If we want, we can simplify it maybe to look like this, because we know that G is 9.81 and we have to multiply that by M. But right now, that's as far as we can take it. Okay? Good there? All right. Tension forces. We said that tension is a force. Tension forces are pulling forces. That's what strings do. They pull on objects. So this one that's labeled A over here, we would draw the arrow in this direction. That's the way that A is pulling on the wrecking ball. So we can label that as the force coming from cable A, right, F of A. And in that problem, they told us how much force that was, right? So this is going to be 460 newtons. And then the last force, right? Cable B, again, tension is a pulling force, so it's going to pull in that direction, right? But do we know how much that force is right now? That's one of our unknowns, right? That's what we're looking for. So we can't really label that force. I mean, I suppose if we wanted to, we could, never mind. If we wanted to, we could label it as F of D, right? Because that's what we're looking for. But that's about it. All right, good there? We've drawn our forces. We've identified what we're looking for. We've identified what we know. Right now, let's go in the next direction. Is this wrecking ball moving as it hangs here? No, right? Therefore, we just learned that if an object is not moving, it is in equilibrium, right? That the net force has to add up to 0. And that means that if we take F of G plus F of A plus F of B, that all together, those three have to equal 0. Right? Now, in this case, is it going to be as easy as just adding up the numbers and getting, whatever's left over? Right? Can't do that in this case because they all don't lie on the same line. They're not all x-axis or y-axis, right? So we said when that's the case, if we can't just add up the numbers, vector addition tells us that we can take a look at each axis separately. That if we look at the x-axis, and we have equilibrium on the x-axis, and then if we look at the y-axis, and have equilibrium on the y-axis, then overall we have equilibrium. Remember last chapter, if we had forces that weren't perpendicular and weren't all lined up on the same line, we break everything up into its components, and then we add the x's and add the y's, right? Does that sound familiar from last chapter? Hopefully, maybe. All right. X-axis, we have this force that's labeled A on the x-axis, right? But do we have any other forces on the x-axis? Not right now. Y-axis, we have this gravity force, but any other forces on the y-axis? Not right now. But then we have this B force, right? And it's not on the x-axis or the y-axis. So we said that in this case, right, if we have a force that isn't on either x or y, what do we do with it? If we have a force that's pulling up and to the right, really, that's a combination of this one and this one, right? We called those the what? Remember the name of those two? Not the resultant, the component vectors, right? So those are the two components of B. The components lie along the x-axis and the y-axis. So by taking B and breaking it up into its components, now everything either is on the x or the y. Remember that components are basically the equivalent of this force. So breaking something up into its components is like the equivalent of this. So now on the x-axis, how many forces do we have? Now there's two, right? We have that force of A plus we have B, but it's not all of B, right? It's only what? Not necessarily half,
Horizontal.
but the horizontal or the x component of B. Those two together have to equal 0. And then on the y-axis, we have another two forces, right? We have gravity on the y-axis plus f of b, but it's not all of f of b, right? It's just what? The y component, and those two together have to equal 0. In the past, I've usually given you the hypotenuse of the triangle and an angle and made you find the two components. But do we know the hypotenuse here? We don't. So I can't do it that way. But if we look on the x-axis, right, how many forces are on the x-axis? Just 2. What do they have to add up to? 0. If we have two forces on the x-axis, one points left, one points right, they have to add up to 0. If we know the one that points left, guess what the one that points right has to be? It has to be the same, just in the opposite direction. So, without writing that all down, right, I'm just going to make this assumption that now we know the x components of, go ahead. Technically it would be negative, right? Now, we talked about the idea though, it would be negative if we were doing it in terms of this equation, right? But from the picture, we can kind of tell which way it goes anyway, right? So if you want to make it negative, that's fine. Or if you want to make the red one negative and then the blue one would come out positive, that would be fine too. If that makes sense to you, go ahead and do it, okay? Because technically, that is the case when we talk about it in terms of the equation, okay? If that makes sense, flowing from the last problems to this problem, fine. Okay, we okay with that? But, is that what this question asked us for? It didn't ask us to find the x component of b, it asked us to find b. So, let's do this. See if I can get this to work. Oh yeah. Kind of on fire today with the board. It's just, so you know, grabbing all the right things. So, this is just the same drawing as here, right? I just brought it out here so we can work with it a little bit more, okay? We just learned that this component here is 460, okay? And even though it didn't come with my cloned version of this, we learned, or the picture told us, that this angle here was 40, right? Most of the time that we found out, or most of the time that we were using and finding components for vectors, right, we had this in the form of a triangle, yes? Okay? So we can move that y component over here and make a triangle out of this. And now we have a right triangle where we know one of the sides of the right triangle, and we know the angle of the right triangle. So what can we find? If we know one side and one angle, We can find the rest of the triangle, right? All the other parts. In this triangle specifically, which part of the triangle are we looking for? The hypotenuse. What side do we have in relation to the angle that we know? Opposite. So what trig function are we going to use? Which trig function has opposite and hypotenuse? Sine, right? Now, watch this real quick because people make mistakes with this, okay? Sine of theta is defined as opposite over hypotenuse, right? We're solving for hypotenuse in this problem. Most of the time that we've done this previously, I was asking you to solve for one of the sides of the triangle. But this time we're solving for the hypotenuse. Hypotenuse is in the denominator of this fraction, right? So we got to get it out of there to solve for h. First thing I'm going to do, I'm going to multiply both sides of that equation by h. If I multiply both sides of that equation by h, cancels here, right? And we're left with this. Yes? And then, to get h by itself, what are we going to do? Divide both sides by sine theta. So whereas in the previous problems, generally when we were looking for the two sides, we would multiply. Here we need to divide. So the hypotenuse of this triangle, we know is f of b, right? We learned that the opposite side of that triangle is 460. And we know that the angle that they gave us was 40, right? So now we can find out what f of b is. $7.16. All right. Does that make sense? We okay there? Questions? All right. Are we done with this problem, though? Not done with this problem. If we go back up to our original drawing, it also asked us to find the mass. The mass, we know, influences the amount of gravity that is acting on an object. Where is gravity showing up in our picture? Which axis? Y-axis. We've already established that we know that there is equilibrium on the y-axis. So, if we can use the y-axis to solve for what we need to solve, or to solve for what we need to solve for, we can get the mass. Two forces on the y-axis. One points up, one points down. What is that going to mean about those two forces? They got to be the same, right? Because we got to end up with 0. But do we know either of those forces right now? Yeah. Well, do we know either of these y forces? At this point, no. But this y-axis force right here is a component of B, right? Going back down to this triangle, we've already figured out that the hypotenuse is 716 and the opposite side is 460. Can we figure out what the adjacent side is here? Sure, there's a lot of different ways you can do this. You can use cosine, you can use tangent, you can use Pythagorean theorem. Any one of those three should get you this side of the triangle. And this side of the triangle is the y component of B. So pick one. It should end up in between 460 and 716. I think, is it 542? Is that what it ends up being? Anybody actually run it through yet?
What?
I got 548.
548. this triangle is 548. That y component is this force right here. If we go over back to this equation, right, we know that there has to be equilibrium on the y-axis. How many forces are there on the y-axis in this problem? How many forces on the y-axis here? 2, right? One point's up, one point's down. If we know the up one, guess what? We know the down one, right? So that means that f of g has to have a value of 548, right? And then here, like, you know, we could call that negative if we wanted to, right? If we call this one positive because it points up, okay? But that's not what this problem asked us for, right? What did the problem ask us for? It asked us for the mass. We know that f of g we can calculate by 9.81. Okay. And then handle, like, if we call this one negative, right? Because this 9.81 is a downward acceleration, it would also be negative too, right? Because if we didn't, we'd get a negative mass, and we can't have that. Okay. And then, I think, if I remember correctly, it's 55.9.
Yeah.
Right? And then that would be kilograms, right? Because we're solving for the mass, not a force. Good there. All right, let's do one more example. A little different than this one, but very similar to one that you're going to see over in the lab. Not the top of the next page, that one's kind of boring, but this one here, oh boy, is a good one. All right. An adventurous archaeologist. No names, please. Right? Just happens to be wearing a brown leather jacket, a brown fedora, and has a satchel.
Indiana Jones.
So, no, it doesn't say that. It just says an adventurous archaeologist, right? It's completely coincidence that Indiana Jones carries a satchel, right? That we learned that in Hangover, right?
Oh yeah, he's like, who was a
Satchel. Indiana Jones wears one. All right. Anyway, so adventurous archaeologist must make his way between two cliffs. A rope is suspended between the two cliffs, and the archaeologist starts to make his way across the rope. In the figure to the right, he is exactly halfway between the two cliffs. His mass is 81.6 kilograms. If the ropes make an angle of 15 degrees below the horizontal, which is labeled as theta in this picture, what is the tension in each side of the rope? So, I'm actually going to do this a little bit backwards. I'm going to draw the picture first, and then we'll talk about what we're looking for. So, archaeologist hanging here between these two sides of the cliff. Forces that are acting on said archaeologist. What can we put in first? Gravity, definitely, right? So we got to take into account gravity here. Gravity's pointing in this direction. And we've learned, right, that to calculate that force of gravity, what do? mg, right? The mass of that object times 9.81, or the acceleration of gravity. Do we have the mass of the object here?
Yeah.
It was given to us in the problem. So we can figure out what f of g is, and I think, if I remember correctly, it's like 800.5, is that right? Now, to finish this off, right? It says, what is the tension in each side of the rope? Remember we said tension is force, and tension is a pulling force. So each side of this rope is pulling on the adventurous archaeologist. Right? One pulling this way, one pulling this way. Right? If we want to, we could label this F1, and we could label this F2. If the archaeologist's is halfway between the two cliffs, we can probably make a pretty educated guess. How are F1 and F2 going to compare to one another? If he's exactly halfway, probably going to be what?
Equal.
Probably going to be the same. Okay? Also, it told us that being halfway across, these two sides of the rope make the same angle with the x-axis here. They go down exactly the same amount. Another indicator that we're probably talking about the same amount. Okay? All right. If this adventurous archaeologist is hanging there motionless, right? He's got to be in equilibrium. And therefore, the net force equals 0. And so, F of G plus F1 plus F2 all together have to equal 0. Right? That's what net force equals 0 is telling us. Now, we just talked about the idea that F1 and F2 are going to be the same amount. If we know F of G, can we just split F of G in half and call F1 half of it and F2 the other half of it? No. It'd be so easy if we could, right? But F1 and F2 are not directly opposites of F of G, so we can't do that. But we did talk about the idea that we can split up these forces, x-axis, y-axis, right? That's how we do vector addition in 2 dimensions, right? Look at the x-axis stuff, look at the y-axis stuff. Forces are vectors, so we can do that here. But, just like we did in the last problem, F1 and F2, neither one of them is on the x-axis or the y-axis. And that means they have what? They have components, right? F1 has a component that goes this way, and a component that goes this way. F2 has a component that goes this way, and a component that goes this way. Thanks, not that way. This way. Alright, good there? Now, in this case, right, we only know one force, and that's gravity. So what do you think, which side are we going to work with here? Probably X or Y. Let's work Y. As we look at this picture now, how many forces are there on the y-axis in this picture? 3, right? We've got gravity pulling down. We've got the y component of F1 pointing up, and we've got the y component of F2 pointing up. Yes, they are in the same spot, but they are 2 different forces. So, this y-axis, we have F of G plus F1 along the y-axis plus F2 along the y-axis, all together have to equal 0. Alright, now I'm going to ask you to make another jump without writing down a bunch of things. If the angles that these 2 forces are below the x-axis are the same, and we use that angle to make a triangle, what do you think is probably going to be the case about those 2 components? Same angle, we said that these forces are going to be the same. What's going to be true about these components? They're going to be the same as well. The same as each other. How many up forces do we have in this picture? 2. How many down forces do we have in this picture? 1. So if this down force is 800.5, and we have 2 up forces,
400.
and in this case they have to be the same, how much does each one of them have to be, Joe?
400.25.
400.25.
400.3 with sig digs, right?
We'd probably actually go 400 with sig digs because there's only 3 sig digs here. So this would probably be
Yeah, Joe.
801. Actually, we'd probably round that to, so we'd probably go 400. 401, I guess sig digs, but then we'd lose a little bit. So
Yeah.
I won't be real picky about that here. So this one's got to be 400.25, and this one's got to be 400.25. Does that make sense? Why? 2 up forces, 1 down force. If we reason that these two have to be the same, they're each half. But it's not what this question asked us for, right? The question asked us for what is the tension. So let's take this. Let's take these. Bring this down here. Does it matter whether I take the blue or the red?
No,
They're
they're
the same, right?
Tickles your fancy.
So we know that this side here was 400.25, right? It told us that this angle, the problem, that angle is 15. We'll bring this component up here. Not that it really matters, right? Because what are we really looking for in this problem? What part of the triangle? Looking for the hypotenuse, right? In relation to the angle that we know, what side do we know? Which side of the triangle do we know related to this? Opposite, right? So again, sine of theta equals opposite over hypotenuse. Multiply both sides by hypotenuse. Divide both sides by sine of theta. Something? 1546?
Yep.
Questions?
Would one be positive and one would be negative, right?
In this case, no, because here, remember, this F1 is actually this angle, right? So because it's not on an x-axis or a y-axis directly, we can't really use positive or negative to answer that. The direction comes from that angle, which it's below the horizontal and stuff like that, okay? So in this case here, I'm really only concerned about values, right? I'm only going to be concerned with magnitude at this point, right? Good? All right. Again, we make use of the fact that we have to have equilibrium on the x-axis and equilibrium on the y-axis in order to have total equilibrium. That the net force has to equal 0 on the x and the y-axis. You are going to make use of that today in doing our lab. Over on the other side of the room, I have set up 6 stations. At each one of those stations, there is some combination of tension, gravity, normal force, and friction, and/or friction, that results in equilibrium. At each station, those masses are not moving. Therefore, they are in equilibrium. So we're going to make use of the fact, we're going to find equilibrium on the x-axis, equilibrium on the y-axis, in order to find some specific values of forces. Okay? At each station, I have labeled which station that is. So there's a piece of tape on the table that says station 5 or station 4 or whatever it is. I have also given you the mass of the object that is at that station, because you're going to need that, except for one spot, because one spot you're supposed to find the mass of that object. Okay? Also, at a couple of the spots, you will see there are some springs, and those springs are used to measure some of the actual forces that are acting at that station. So in some cases, I will give you the force that that string is pulling. And you'll need that then to maybe find components or something like that. Okay? Good there. All right. We have 41 minutes until the bell rings. All right? You'll have the rest of the time to work on this. I'll be around with questions. Oh, you will have to make some angle measurements. Protractors are in the drawer underneath the window over there. Okay? You will also find at the stations that there are sometimes there's a fishing line hanging down that has a small weight attached to it. Like this one right here, it's got this small weight. That is just there to represent the y-axis. So you can use that to make a measurement and make sure that you get a more accurate reading with the angle. Okay? Good there?
Yeah.
I'll be around to help. Ready, set, go.